Welcome to the DemystifySci podcast. I'm Anastasia.
I'm Shiloh.
This is the podcast where we explore the ideas that we think may change the world. What this means is that we have to talk to a lot of people to find what those ideas are. And today we are sending you this broadcast from the sunny shores of the Corinthian Gulf in Greece. What are we doing in Greece, you might ask? It's a very good question. Number one, we have our Beyond the Big Bang conference in Portugal in a little less than 3 weeks. And so in anticipation, we figured that we would take a tour through the land that gave us the first atomic theories in history. And in anticipation of this tour, we lined up a couple of conversations with physicists. Last week, we released our conversation with Steve Wolfram. This week, we're releasing a conversation with Jacob Barandes, who is a professor of physics at Harvard University. And Wolfram and Barandes represent the polar opposites of a debate about the nature of reality that has been going for 2,000 years. In a couple of days...
I would say much longer than 2,000 years.
You think so?
I think so. I mean, the early atomists like Democritus and Leucippus are back, at least 2,500 years, and they probably got their ideas from someone else. The point is that this has been going on forever, and we wanted to trace the roots of it.
And there's this question, is the substance of the world actually substance, or is it ideas and forms that push matter around in some indescribably complex way without there being a really clear bridge? And so if you listen to our conversation with Wolfram last week, it's pretty obvious that Wolfram falls into the camp that reality is computational, mathematical. Everything is made of these hypergraph structures that aren't actually things, but somehow eventually end up producing things, and it's very idealistic. And Barandes, professor of physics at Harvard University, has the total opposite perspective. His view is that no, there is mathematics that describes quantum mechanics and fundamental physics in the same way that you would describe a classical system, which is made of bodies in space doing things, and we have somehow completely left behind that attempt. And our conversation today is all about his work in revitalizing that effort, because there's not that many people in the world that are substantialists, and hopefully he'll forgive me for pinning him as one. But I think that this is the fight that has been going on for millennia. Is the world's substance, or is the world's math?
And I think we come down somewhere in the middle. I think we find a good use for mathematics and for other descriptive systems beyond physics in making sense of this world we live in. But at the end of the day, it seems like physics, being physical objects doing things, makes me a lot more comfortable. Leave everything else to somebody else. Leave it to the artists. Leave it to the poets. And of course, Greece has plenty of both. So we'll be exploring that in the days to come. We have some debrief episodes comparing these two perspectives coming to you soon as well. By the way, if you do want to make it out to Portugal in just a few weeks, there's some tickets left. We're putting on some really cheap discount tickets if you want to basically just come by for the talks and get your own lodging, get your own food, and we'll make it affordable so you can join us. So check that out. We'll put links in the description. You can go to DemystifySci.com to find out more.
And if you cannot make it to Portugal, I would strongly encourage you to join our Patreon for 75 cents a week, which is almost nothing. You give us the ability to travel the world, to talk to people in person, and to really map out this weird world of ideas and theories that is going to shape the future. And so a huge thank you to everybody who's already joined us. We love meeting with you guys once a week on Sundays. To anybody who has not joined us yet, patreon.com/demystifysci. And I hope we see you there.
Enjoy the conversation with Jacob Barandes, and we'll see you next week.
The scientific revolution starts now.
The DemystifySci podcast.
Let us see in the dark.
We have come from the faraway land of Oregon, and we're very excited to speak with you. In part of our preparation for this meeting, we watched a conversation with our friend Kurt Jai-Mongol for Theories of Everything, which was an excellent conversation. I was struck by the just incredibly layered and yet straightforward way that you present what is a very complex history of a very complex field. And I don't want to go over the same ground that you guys went over with Kurt, so I want to start with sort of a framing question so that people can understand what we're going to be talking about without necessarily having to rehash the entire history of quantum mechanics. From the conversation, I gathered that most of what we will talk about today will center around Hilbert spaces, Markovian dynamics, and indeterminate stochastic processes. Indivisible stochastic processes, that's right. And so I wonder if we could start just by talking about Hilbert spaces, giving people a ground level understanding of what they are for quantum physics, why they're so important, before we move on to why you think that they might not be what consensus says that they are.
When modeling any kind of physical system, describing in theoretical terms some kind of thing out there in the world that physicists may be interested in, one of the starting ingredients is, what is the menu of possibilities? What are the possible things that can be related to each other through time, through maybe interventions by experimenters, the possible arrangements or configurations or states of the system. And every physical theory we have at some point proposes this menu of possibilities. When we think about classical physics, and by classical I mean the physics that predates the introduction of quantum mechanics in the 20th century, the space of states is the possible set of all configurations a system can be in, and depending on how one is modeling the system, each state may, in addition to including the configuration or, say, position or arrangement in space of the ingredients of the system, may also include the momentary or instantaneous rates of change of those configurations. So in Newtonian mechanics, we're imagining that our systems are bodies in space. The set of states is every arrangement of those bodies in space and their velocities, their instantaneous rates of change. In the textbook way that people teach and use quantum mechanics, that somewhat familiar-looking, straightforward space of states, the state space that one uses in Newtonian mechanics, is replaced by a much more abstract kind of state space called a Hilbert space. The Hilbert space of a quantum system is a mathematical kind of space. It's called a vector space. But the vectors here, the idea of vectors goes back to the idea of like literal arrows pointing in various directions in physical 3D space. A Hilbert space is a mathematical abstraction of this idea of a space of arrows. Rather than the arrows in three-dimensional space, in a Hilbert space, the elements are abstractions of arrows called vectors, and the number of dimensions depends on the kind of system. For very simple systems, the simplest kinds, these spaces could be two-dimensional, three-dimensional. For a qubit, a single qubit has a Hilbert space that's two-dimensional. The directions, the perpendicular directions in this space correspond to what the qubit is like up or down or on or off. But for more complicated systems, the Hilbert space can be very high-dimensional. In addition to being high-dimensional and abstract, Hilbert spaces also incorporate the complex numbers. These are ordinary numbers, as well as ordinary numbers multiplied by an abstract mathematical ingredient, little I, which denotes symbolically the square root of -1. Complex numbers have a reputation of being somewhat exotic. They have a very interesting history, but these are incorporated into the Hilbert space as things that you can multiply these abstract vectors by. Hilbert spaces also come with a rule for taking two vectors and combining them to get in general, a complex number. There are a couple of other mathematical ingredients you need, but the textbook postulates or axioms of quantum mechanics take the Hilbert space as the basic set of possibilities out of which all the other mathematical ingredients come.
Can you tell people a little bit about the advantage of complex numbers and just, moving the abstraction deeper into the quantum world? Why is that necessary? Is there a way to put that in a phrase or a few sentences, or is it something that can only be understood through quantitative logic?
The role and necessity of the complex numbers in quantum mechanics is a complicated, complex question. People have been debating it for a long time. When Schrödinger introduced his eponymous Schrödinger wave function, this thing that is an element of the Hilbert space and changes with time and from which we extract predictions of measurement probabilities, he noted that his wave function involved the complex numbers. He was somewhat bemused by this. He didn't understand why this thing had to involve the complex numbers. They just came out of the mathematics. And there's a letter that he wrote around that time in which he said, surely this wave function must be a real quantity. So he was quite confused about why the complex numbers appeared to be so important. I don't think there is a consensus on exactly why the complex numbers are so important in quantum mechanics, but there are a lot of important places where they show up. I can say a little bit about some of the places where the complex numbers show up if you'd like.
Do you generally associate them with cyclic trigonometric situations? Like, I often see complex numbers introduced in phase of electric circuits, things like this. Is there something to the cyclicity of it?
So, every complex number, by construction, corresponds to a point in the plane. I can say a little bit about the complex numbers now, if that's okay. I don't want to go too far into the weeds of the mathematics, but so
the reason that I ask, I'm not just trying to chase a rabbit hole, but I do think there's a really interesting break between classical mechanics and quantum mechanics that involves this transition into imaginary spaces in general. And I was wondering if we could peel that back a little bit.
So the need for these sort of abstract mathematical spaces, the complex numbers are a kind of abstract mathematical space. Hilbert spaces are a kind of abstract mathematical space. There's a related notion called a configuration space that also shows up, actually in classical physics as well, but also shows up in quantum mechanics. That's also a kind of abstract space. And one can get even more abstract. There's a space called operator algebra. The most relevant kind of operator algebra to quantum mechanics is called a C-star algebra. And there are von Neumann algebras, and one deals with a lot of very abstract kinds of spaces in quantum mechanics. There's a trade-off here between the clarity of the physical picture and the convenience and power one gets from certain mathematical tools that are inherently abstract. So you're exchanging concreteness for mathematical convenience and mathematical power. And quantum mechanics really takes this to a pretty severe extreme. Before quantum mechanics, we still also make this trade-off. You can take ordinary Newtonian mechanics, bodies in space, and reformulate it in a very abstract mathematical language.
Is this the Lagrangian?
The Lagrangian approach is one example of this sort of abstraction. Even more abstract is the Hamiltonian approach. And even more abstract than that is the Hamilton-Jacobi approach. And interestingly, it was the Hamilton-Jacobi approach which suggested to Schrödinger his introduction of wave functions in quantum theory. So the Hamiltonian and Hamilton-Jacobi approaches were, in the early days of quantum theory, the bridge that led to the development of the theory. The theory was originally formulated in a language that was taken from the Hamiltonian formulation of classical mechanics and the Hamilton-Jacobi formulation. These are very abstract. We typically don't teach these to introductory physics students. So it's, in some ways, it's not surprising that quantum mechanics should be so abstract, because its origin story comes out of the most abstract representations of classical physics.
Interesting. And you're also trying to say so much, having such a difficult time seeing what's happening at that scale as well. You're taking these experiments and trying to, I don't know if deconvolve is the right word here, probably not from a mathematical standpoint, but you're trying to read really heavily into these. And so I assume that finding patterns amongst the relationships from the measurements is ultimately something that needs to be simplified and coordinated and requires higher and higher levels of abstraction.
I mean, reading patterns directly out of these mathematical abstractions is difficult and arguably misguided.
But popular?
Popular. So if you take, say, Newtonian mechanics, so bodies in space, bumping around, moving around with velocities, with accelerations, forces between them, and you reformulate your Newtonian theory in this very, very abstract language, you see mathematical entities that don't have a clear ontological meaning, ontology meaning like what's really out there, what really physically exists. So an example would be in the Hamilton-Jacobi formulation. We introduce this very bizarre-looking partial differential equation. It's got not just derivatives, but partial derivatives. It's a multivariable equation, and the solution to this equation is an abstract function called the Hamilton's principal function or the Hamilton-Jacobi function. And you can use this as a tool to predict how rocks will move, how planets will move. But if you attempt to reify this mathematical function, if you attempt to regard it as like a part of the ontological furniture of reality, I think that's a mistake. I don't think that the Hamilton-Jacobi function is like a rock, is like a physical object.
Well, can we talk about reification in general in
Yeah.
quantum mechanics? Because I feel like this is something that the popularizers of quantum mechanics have perhaps led the charge with. You know, even the concept of a particle at some level, when you start to really press on it, you realize it's more of a dynamic of some sort. There's a momentum quality to a particle. It's not just a statically conceived object like a table or something, right? And so I feel like people have grown, and I don't know how much this is true on the inside at the level you're at, but it seems like on the surface, you know, with people studying quantum mechanics for the first time, or even high school students being introduced to these basic principles, they think of a particle as like a mote of dust or something, right?
Yeah.
And it's not exactly what we're talking about here, right?
I think when newcomers to quantum physics, students arriving in college, or reading a textbook on quantum mechanics for the first time, or just members of the general public, think about quantum mechanics, I'm not going to presume what people think about it. I can only talk about my own experience, which may be more or less typical. I heard about quantum mechanics in popular books, in magazines. I learned a little bit about it in, documentaries. And the picture that I got about quantum mechanics was, we start with the classical world of macroscopic reality, the world around us that we human beings see. And this world is populated by objects, people, tables, chairs, rocks, cars, airplanes.
Bodies.
And these bodies have locations in physical space. They are somewhere. And the bodies move. They have some notion of movingness, of motion, of behavior. That behavior is characterized by a speed, by a direction. And in the classical world, the motion or behavior of these bodies is sometimes unpredictable, but more or less it follows continuous paths. until it bumps into something, right? Things move in reasonably continuous, predictable ways until they bump into something, or if they're buffeted by the air, then they move in a somewhat more chaotic way. And I think the first idea that many people have about quantum physics is that it's about microscopic things. If you consider objects that are not human scale, but are much smaller, if you imagine considering a succession of smaller and smaller objects, then they still have something like locations and something like motion, but the motion becomes jittery. It becomes more random. There's this idea that at the micro scale, you still have ingredients of reality with locations, but their motion has become much more chaotic. It's almost vibrating, and things are bouncing around in unpredictable ways, much more unpredictably than objects on our macro scale. And you can't ever get these objects to come completely to rest. You hear things like, oh, there's an uncertainty principle. You can't either know exactly where an object is located and what its momentum or velocity is, or maybe it's more than just knowledge. Maybe physically, ontologically speaking, this object simply cannot have both a location and a definite kind of motion, a definite velocity. So maybe if you attempt to zoom in on small enough objects, what you find is that to the extent they have a well-defined location, they're kind of vibrating very quickly, or they're moving in some uncontrollable way that encodes or is constrained by this uncertainty principle, this relationship between not being able to have a precise location or position and not being able to have a precise velocity. This is not the picture of quantum theory that one gets from reading textbooks or taking coursework. The textbook version of quantum theory, based on postulates or axioms laid down by Paul Dirac in his book Principles of Quantum Mechanics in 1930, and John von Neumann in Mathematical Foundations of Quantum Mechanics, his book in 1932. That picture is radically sparser, more arcane, does not paint a world picture at all. Instead, what that theory says, the textbook theory, is every system has this abstract space called the Hilbert space. We represent the current state of affairs of the system using an object, a mathematical object, not a physical object necessarily, but a mathematical ingredient of this Hilbert space. Any question you want to ask about the object, any observable feature, is represented by another kind of mathematical ingredient obtained from this Hilbert space. And then there are formulas. You combine these two ingredients, the feature or ingredient that represents the state of affairs of the system, of the object that you're trying to model, and then the ingredient that represents whatever observable feature you're trying to learn about. And there are formulas that combine these ingredients, and they generate a probability. A probability for obtaining a particular measurement result, if we were to measure that property, with a particular measurement probability. The formula for that measurement probability is called the Born rule, named after Max Born. Immediately subsequent to obtaining the measurement result, the result is locked in through a process called reduction or collapse. The ingredient representing the state of affairs of the system suddenly changes to lock in the result so that if you were to go and measure the same observable feature again, right away, without giving the system any time to do anything else, you would be nearly certain to get the same answer you got before with nearly 100% probability. What I've just told you is the axioms. There are some additional technicalities about what it means if you've got two systems, how we're supposed to think of two systems as being combined into one system. But basically, I've just given you everything that the textbook theory says about reality. What you'll notice is there's no world picture. There's no discussion of bodies in space. In fact, there's really no discussion of physical space really at all at that level of generality. When you model an actual physical system, you do have to specify that some of the observable features are related to space. But at no point are you saying that the object is in physical space, that physical space is a place where things live or where they are. There's no discussion about objects having locations or moving anywhere. All the theory says is that we have these mathematical ingredients and a rule for predicting what will happen when we do measurements. These axioms do not tell you what a measurement is. You just have to identify a measurement as something that you know it when you see it. Like the old statement about obscenity. Obscenity is something that, I can't define exactly what's obscene, but you know obscenity when you see it. And the same thing is supposed to be true for measurements.
Well, isn't it kind of that the measurement is the process that causes collapse, and anything that doesn't cause collapse does not constitute a measurement?
In a way, yes. But that's just circular. Measurements are the things that cause collapse, and the axioms say the collapse follows a measurement.
Well, I've always interpreted this to suggest, and okay, so this is a little bit difficult because in the conventional quantum picture, there is not a base reality that you're interacting with. And so it feels like saying that, okay, your measurement device has properties that interrupt the system because the process of measurement either reduces its angular momentum or disturbs the space. Like, to me, that seems like not necessarily a circular argument, because if you have physicality involved in it, I'm like, if you have a buoy on the surface of the ocean, and the buoy is able to tell you the height of the waves, then that's a measurement that is not necessarily disturbing the system. But if you have, let's say, a seawall, the seawall is inherently disturbing the system, and so if you put this down back into the realm of quantum, something that's like the buoy that floats on top of it that's not disturbing it, not a measurement. Something that crashes the system, causes collapse, is a measurement.
Yeah, so the difficulty here is, I think you've put your finger on it. There are some processes that count as measurements, and other processes that don't count as measurements. And the axioms don't provide us with a way to distinguish between the two. Now, I think, so let me just say that one view about this, I think there's a view about this that is best explained through a metaphor. Let's suppose that I am a pollster. I'm a pollster. I am going to conduct a poll of an electorate in advance of some kind of election. And I want to predict how I think the election is going to turn out. So I formulate a probabilistic model. This model begins with survey questions that I'm going to give to some group of people. I will lay out the methodology by which I'll attempt to select a representative sample of potential voters. I'll collect the data, subject them to some kind of rigorous analysis. I'll use the latest statistical methods that I'm getting from very good textbooks. And then the goal is to make a prediction about the what's going to come out of the election, some statistical prediction. There are going to be error bars, there's going to be all kinds of estimating involved. And maybe I'm feeling pretty proud of this model I've set up. I feel like it's pretty robust. And then someone comes along, a critic comes along and says, your model is no good. And I ask, what's wrong with it? It all seems to make sense. I've tried it a bunch of times. It's given very good predictions of past elections. I'm using the latest methods from statistics. What could be the problem? And the critic says, well, you failed to model the pollster and the polling process itself. I'm looking at all of your modeling and probabilistic, the whole, everything you've laid out, and nowhere in there do I see how the pollster is being modeled or how the polling process is being modeled. And I would react by saying, well, you're asking too much. This is this is just a model of polling an electorate. I don't need to include what's going on in my brain and in my body. I don't need to include the methods I'm using and how I'm doing, obviously you have to include in the probabilistic model decisions I make about whom to poll, but you don't need to know like how I get up out of my chair. You don't need to know what kind of paper I'm using. Like all these details are irrelevant. My model has a very narrow purpose, and it is accomplishing that purpose. I mean, what do you think I'm doing? Trying to write a probabilistic model of all of microphysically precise reality? I'm not a quantum physicist. Okay, and then the critic says, all right, you're right, I'm sorry, I was mistaken. And then the critic goes and talks to a quantum physicist and asks exactly the same questions. You quantum physicists, you're modeling a measurement process. You're measuring some system. You have the rules of quantum theory as laid out in that textbook that we talked about. Dirac-von Neumann axioms, the orthodox approach to quantum theory. And this describes how you will survey nature and collect data and make predictions. But you fail to model yourself, the measurer, the observer, the agent doing the measurements or interventions. Now, the quantum physicist can't turn around and say, oh, well, that's asking too much. This isn't supposed to be a complete oh, wait a second. This is supposed to be a complete microphysical theory of reality. I guess I should have to model myself, right? And so I think it's entirely reasonable for a quantum physicist to ask exactly those questions. There's a tradition in analytic philosophy, in foundations of logic, foundations of mathematics, and computer science, that when you have a very grand theoretical framework, one that's supposed to be all-encompassing, that you run into trouble once you start plugging the features of the framework back into itself. You get these self-referential problems. Famously, Russell's paradox in set theory. What happens if you try to construct a set containing all sets that do not contain themselves, right? There's a self-referential problem that leads to some real problems with set theory. Gödel has his famous pair of incompleteness theorems, and one way to think about those incompleteness theorems is that they arise from a kind of self-referentiality, where you construct certain statements that you feed back into themselves. The halting problem, which establishes fundamental limitations to what we can say about computer programs, can also be understood as arising from a kind of self-referentiality, where you propose a certain kind of computer program and then feed the script of that program back into itself. The same thing happens, arguably, in quantum theory, and is at the heart of the basic problems of quantum theory. It's purportedly a complete theory of microphysical reality, which means it should include observers and their process of measurement as well. What if I attempt to model, as part of my quantum system, another person, a second observer, maybe someone sealed up in a box for the duration of the experiment, so that I can keep the whole thing shielded? And now what I'm doing is reconstructing the Wigner's friend thought experiment. I want to now model this other observer in the box using quantum theory itself. And I run into ambiguities about exactly which axioms I'm supposed to use and how I'm supposed to use them. It's a kind of self-referentiality problem.
But that's an artifact of there not being a base reality, right? Because with Wigner's friend, the Wigner's friend thought experiment, as I understand it, is that there's Wigner on the outside of the box, the friend is on the inside of the box, it's perfectly sealed. He does a quantum measurement, and then has the quantum measurement happened for Wigner? Has it collapsed? And I'm like, if there's a base reality that something is actually happening when you stick the measurement device into the system, then it seems plausible that there's no paradox here, and it's like, well, of course the base reality has resolved, and it's the same for everybody. But is that just like a totally facile interpretation of the situation?
I think one should distinguish between what actually happens and what the theory is supposed to say will happen.
But isn't that the test of a theory? Is like, does it line up with what makes sense in terms of what would actually happen if you had the ideal closed room?
Yeah, so ostensibly, if you were to do this experiment, one and only one thing would truly happen. The question is, does our theory unambiguously tell us what that thing is, or is the theory limited in some way? Arguably, the textbook theory is limited and is unable to yield a definitive, unambiguous statement about what will happen. Although, presumably, when you actually do this experiment, if you could, one particular thing would happen.
Why is it that the theory doesn't tell you what will happen? Because as far as I can tell, measurement produces collapse. If the friend inside the box has measured it, how does that not lead the theory to say that collapse has happened?
Because the theory doesn't provide us with a rigorous definition of exactly which processes are measurements and which ones are not, there's an ambiguity. Wigner may not be sure that the thing the friend did constituted a measurement. Perhaps the friend is not a person. Perhaps the friend is a tardigrade, one of these extremely tiny organisms. Or maybe the friend is an amoeba. Or maybe the friend is a complicated arrangement of buckyballs, or carbon nanotubes, or perhaps the friend is a small collection of electrons. At some point, we say that the interaction between the friend and the quantum system the friend is measuring inside the sealed box does not count as a measurement. And above some threshold, we say that it does, but the theory doesn't tell us what that threshold is in any precise way. And we have to either apply the collapse axiom or not. There's no halfway version of this axiom.
And there's no scale that is known to cause collapse. Like you need at least one atom, or you need at least 10 atoms.
There's no rigorous Heisenberg cut, a dividing line that says systems simpler than or smaller than this particular threshold don't produce collapses, and those above do.
Okay, so this is actually something you wrote a paper, I don't know, maybe like 10 years ago. This was like the first paper where you brought out this idea of the Heisenberg gap, is what you called it?
Well, the Heisenberg cut, and I didn't introduce the idea, to be clear. This is an old idea in literature, yeah.
But so do you think that you could maybe lay out the dynamics of that and the challenge? Because Shaila and I, when we've talked about this before, we've called it this like not schism, but fracture at the heart of physics, where I've parameterized it before as the place where you go from kind of this mathematical reality to real reality, and there's not a place where that bridges. And you made this case where you're like, we have to draw this in by hand, and that's a little bit weird because a theory shouldn't have this arbitrarily placed.
Yeah, so one way to think about this is in the language of the Copenhagen interpretation, which is a little bit ill-defined. Different people responsible for what we call the Copenhagen interpretation: Niels Bohr, Werner Heisenberg, Max Born, talked about it a little bit differently. There is a very extensive discussion of the Copenhagen interpretation in one of the chapters of Heisenberg's 1958 book, Physics and Philosophy. The chapter's literally called The Copenhagen Interpretation. That's his view of it. I mean, I can't represent everybody's views, but certainly the way he describes it is there is a classical reality. That's the world that we inhabit as people. Our measuring devices inhabit that world. And classical reality is well described by the rules of classical physics. And I should say classical in contemporary physics parlance includes relativity. Some people think that classical means Newtonian, but in contemporary physics contexts, classical usually means non-quantum. So we allow, for example, special relativity to be part of what we mean by classical. And classical reality is the reality of bodies in space with locations. And the micro world, according to the Copenhagen interpretation, at least as formulated by people like Heisenberg, the micro world is not comprehensible to us with our neural architecture. We can't have a physical picture of the micro world. Instead, we use the abstract mathematical apparatus of quantum theory to predict what classical things will do when they interact with this micro world. So classical objects will interact with the micro world, results will show up on these classical, say, measuring devices, or as seen by classical observers, according to the rules laid out by quantum theory. And the mathematical abstractions of textbook quantum theory are not real things. They're not physically out there. They're just a way that we limited human beings, we classical limited human beings, make predictions about what other classical things we'll see when they interact with these systems. Now, inherent in this story is the idea that there is a classical world that is the world of the big things, and physically opaque world of microscopic things. And what's uncomfortable about that is, well, where's the line? What's the threshold? How small does something have to be before it goes from classical reality to microscopic, unvisualizable reality?
And is that also the line where measurement becomes
Yes.
an action?
That's right.
Okay.
And the Copenhagen interpretation didn't provide anything like a rigorous or a clean understanding of what that dividing line was. And people have talked about whether there really is a fundamental dividing line. Von Neumann formulated it as saying that actually you can put the line wherever you want. You can move it down or up depending on convenience. That it's more of like a mental construct. It's not really out there in nature. But it is a murky thing. And so there is a connection to something else. So if you talk to many physicists, by no means all, many of them, they will say, decoherence solves all of these problems. I think it behooves me to say a little bit about this, because there may be some people who listen to this and wonder, isn't this just solved by decoherence? So decoherence there are rudiments of it in work that goes back a long way, but the first place where it was clearly formulated, at least as far as I know, and from talking to other people who work in foundations and philosophy of quantum theory, there seems to be a consensus among people on this, is that it first shows up in a textbook by David Bohm, 1951 textbook called Quantum Theory. It's right there on my shelf. And in chapter 22, he goes into trying to make sense of the measurement process from within the language of quantum theory itself. He's attempting to grapple with this, treating the measurement process within the formulation of quantum theory itself. And section 22.8 is literally called the physical destruction of interference in the process of measurement, which gets shortened to decoherence. The interference being destroyed is decoherence. And the process is actually simple to explain. When we represent the state of affairs of a quantum system using the ingredients of a Hilbert space, Hilbert spaces, like I said, are vector spaces, and vector spaces have this feature that you can take the ingredients and you can add them together. When each of the ingredients has a somewhat straightforward reading as describing definitively what you would see in some particular experiment, and you add two such things together, you have what is usually called a superposition. And the sum of these things, with numerical coefficients in front, is another valid state of affairs of the system. Now, you might think that all we're doing here is saying the system could be such that a measurement will reveal the first possibility with a probability given by the Born rule, or that it could reveal the other possibility with a probability given also by the Born rule, and the two probabilities have to sum to 1, as good probabilities do. And in fact, that's what you find. With some probability you get this answer, with some probability you get that answer. But what makes this not like an ordinary case of just classical uncertainty about which of these two states of affairs holds is that for certain kinds of experiments, you get cross terms. These two mathematical terms interfere with each other. You do a calculation of certain kinds of questions you want to ask about the system, and you find that you don't get a sum of just two possibilities like you would if these were just classically uncertain. You get additional contributions that come from the two terms interfering with each other. This is called interference and is difficult to make sense of if we try to think of these things in classical terms. Now, if I take my system with a state of affairs represented by this superposition of these two possibilities, and I bring in a measuring device, and I attempt to model this measuring device within the formalism of quantum theory, without treating its interaction as a collapsing measurement, just bring it in and just follow the rules of quantum theory, then what appears to happen is that the measuring device, which began definitively in a state of affairs in which it had no reading at all, evolves to join in the superposition. Now, we again have two terms. In the first term, we have the system being studied with its state of affairs, combined with a measuring device in a state of affairs in which it has read out that result, superposed with the system being studied is in its other state of affairs, combined with a measuring device having recorded that other state of affairs. We still have a superposition of these two seemingly distinct states of reality. If you now attempt to compute answers to probabilistic questions about the system, what you find is those weird interference effects, those cross terms, those additional things that didn't cleanly divide into the two possibilities. You find that they are extremely suppressed. The amount of suppression is exponential in the number of degrees of freedom or moving parts of the measuring device, and for a typical measuring device, the number of individual moving parts, I'm talking like at the atomic level, is 10 to the 23 or more, and also exponentially suppressed in how long this interaction goes by between the measuring device and the system. So you lose these interference effects. They become so suppressed that for any realistic measuring device that interacts with your system, there are no realistic prospects for ever detecting those interference effects. So it's very tempting at this point to say, the interference effects have been destroyed. We call this decoherence. The measuring devices come in, and as a consequence, we're no longer able to detect these interference effects through any practical methodology, experimental, empirical methodology. Isn't that enough? That's originally what Bohm was trying to argue in 1951. Now, there's also a larger environment. The larger environment then interacts with the measuring device, and the larger environment joins in the superposition. Now you've got a superposition of one term in which the system being studied is a particular state of affairs, and the measuring device has recorded that answer, and the environment has now been perturbed or altered by the measuring device, superposed with another term that's analogous, but with all of the results now different. And more the universe sort of joins the superposition, and you just get this bigger and bigger, both terms grow and grow in terms of how many things have been conjoined with them, but they remain always in superposition. The question is, isn't that enough? Now this thing appears to be behaving as if there are truly two distinct possibilities. And can we now think of the probabilities associated with these as just ordinary classical uncertainty probabilities? Isn't that enough? Do we still need the collapse axiom? Do we still need anything else? And people have been arguing about this, I guess since Bohm introduced in a formal way the decoherence process.
I don't totally grasp the difference between decoherence and collapse.
And that's the problem.
Okay.
The problem isn't you. The problem is that
something.
something appears to be missing here.
Okay.
At the end of this interaction, we have this superposition. Now, if you use the collapse axioms, what you're supposed to say is, now that a measuring device has joined the superposition, we collapse the superposition to one term,
right,
with one probability, given by the Born rule, or the other term, with a different probability given by the Born rule. The Born rule is related to the coefficient that was in front. That didn't happen here. Decoherence alone didn't do that. It didn't collapse the thing to one possibility or the other. We maintain the two possibilities in superposition. And that gap is exactly the measurement problem. How do we get from that superposition to a unique outcome, only one of which is realized? What is magical about measurements among all kinds of interactions that causes superpositions to collapse down to one possibility or the other?
Okay, well, if you have a physical system that you're engaging with, and there's some sort of motion that is in the system, which is what is being measured, then doesn't that problem go away because you're suggesting that there's a thing happening, and if you break the thing that's happening, then it collapses, and if you don't, then it hasn't collapsed. Like, I think about this in the sense of, like, imagine you had a camera that was trying to take pictures of a football by throwing rocks at it. Your rock would destroy the trajectory of the football. That would be a quote unquote measurement. But if you have a camera that works like the way that an actual camera does, you have a sensor that reads the photons that hit it, that doesn't disturb the football, ergo it's not a measurement. Is that just a completely naive way of thinking of it?
So what I would say is, what you've provided is a kind of classical like world picture of rocks or photons traveling through space and bumping into things. And the Dirac-von Neumann axioms don't use this language at all.
I know that they don't use that
right.
language, but I guess the thing that it seems like your work is pointing at is that perhaps it is possible to use that language for it because you can arrive at the same mathematical constructs that I don't know. I want to
Maybe saying there's a more generalizable approach to it.
Yeah, what do you think?
Is that reasonable? Right. So this is a framework that has its limitations. It's extremely precise in the job that it does, but perhaps it's not the end all be all framework for understanding.
You mean the textbook approach?
Yeah.
Yeah. I mean, the limitation of the textbook approach is so one view of this is, well, poor Wigner's friend, the friend in the box, is now in this strange superposition of two possibilities. But Wigner on the outside is doing just fine, because Wigner on the outside, if Wigner on the outside uses the Born rule, the two possibilities now behave sort of like distinct classical possibilities. Is collapse ever actually needed? The problem is we're talking about Wigner on the outside. The friend is inside, and the friend doesn't have one. What's going on with the friend, right? That the friend actually in a particular resulting reality?
What sounds like what you're saying is that it depends on who the friend is.
Sure, but I guess the point here is that, like, Wigner on the outside is like the pollster separate from the system being observed. And using the formalism of quantum theory is able to make predictions that seem to work just fine. But Wigner's friend on the inside at the end of this process, it's unclear what is going on with this friend. Is the friend actually in a definite result, but the superposed wave function simply doesn't reveal what that is? If that's the case, we have a hidden variables approach to quantum theory. We're saying that the superposed quantum wave function is incomplete. It doesn't say which of the two realities is there, but there in fact is one of those realities, which we don't know, but one of them is there. Then we're proposing that the wave function is incomplete because there is missing information about which of the results Wigner's friend in fact got. Or both realities somehow simultaneously exist, and Wigner's friend is really in both. There is a Wigner's friend in one reality and another Wigner's friend in the other reality, and then one is proposing something like the many worlds interpretation of quantum theory. Or the measurement somehow magically that Wigner's friend did in fact collapse the wave function, or it collapsed for some other reason. Like when enough degrees of freedom are involved, collapse just happens. Then you're in what's called a dynamical collapse interpretation or theory for quantum theory. You could try to deny that there in fact is any definite answer to the experiment, that no definite answer happened, not one, not multiple answers, that there simply were no answers. But then we run into this dangerous regress, because Wigner could be in a box as well. And if Wigner is also in a box, then Wigner's in the same situation as Wigner's friend. And if Wigner's friend didn't get a result, then there's no reason to think Wigner got a result. And if none of us are getting any measurement results, then we've undermined the entire empirical content of the theory. You have to pick one of these directions. Decoherence doesn't let you avoid picking one of these directions, because decoherence, despite suppressing interference effects, does not by itself single out a unique answer. And because it fails to single out an answer, we either have to single it out ourselves through some kind of dynamical collapse or measurement-induced collapse, or by proposing additional variables, or we have to say that all of the results coexist in some sense. But then one runs into some very fundamental problems about how to make sense of probability. And this is one of the most difficult details. The devil is in the details, as they say. It's one of the places where, when you very seriously try to do this in the many worlds approach, you run into some deep problems.
Because the probability of everything is 1, ultimately.
Well, ultimately, there is simply a unit probability. If you take both realities as exist, then there's just a unit probability, 100% probability, that you end up with a superposition. And what you want is to somehow be able to say, well, yes, but there are two versions or two friends now, and each friend somehow experiences, in some subjective sense maybe, a kind of probability that is not 1. But getting that to work rigorously has proved to be extremely difficult.
Okay, so Shiloh and I last night, as we were thinking about this interview and getting prepared for it, were placing bets about how you see the world that is down below the level of our reality. And the sort of the yes or no, the binary here was, do you think that there are bodies that are interacting at this quantum level to produce the effects that we see? Or do you think that it is, in fact, this something nebulous and mathematical and inherently probabilistic that cannot produce a world picture?
I will answer your question on the condition that after I answer it, you tell me who made which sides of the bet. You shouldn't tell me before.
I thought you were going to say, on the condition that we erase the tape immediately.
Oh, no. No, you can get my answer, but I don't want to. If you tell me beforehand, then it could, in principle, perturb my answer.
Of course.
So let me tell you my answer first. That world picture, the classical world picture we talked about, bodies in space that are moving or exhibiting various kinds of behavior, but maybe down at the microscopic level, there are still bodies in space or something localized in space, things that in some sense are in space that have some kind of behavior, but that this picture, is not a part of the usual way we formulate textbook quantum theory, which is much more abstract. You can view the project that I'm working on as an attempt to salvage the former picture and say that there is, in fact, a concrete physical reality happening down at the microscale, from which the austere and abstract mathematical apparatus of textbook quantum theory can be seen to emerge, rather than taking that abstract framework as being fundamental. This is what I mean when I say that Hilbert spaces in this approach are not real or physical. I'm not saying they're not useful. They're incredibly useful. We should continue to use them. But they're not the thing that should be, as we were saying before, reified. They're not themselves physical. They're just a useful kind of representation of something that deep down is physical. So the view, in a very straightforwardly said way, is there are actually things down there with locations. They could be particles, although I think, given what we're learning about, our best, most successful quantum theories today, like the kind of quantum theory we use to describe fundamental particle physics, is based on quantum field theory. The standard model is quantum field theory, and in fact, rather conveniently, I have a visual aid. This is a mug from CERN, the
Mm.
Particle Accelerator Laboratory in Europe. And there's a little bit of chalk on here, sorry. This here is what's called a Lagrangian density. It's a compact way of encoding the rules that define the standard model of particle physics. And this model is based on a kind of a system called a field. Fields are not objects that move around in space. Fields are localized intensities, but can have other intricate geometric features. They can even sort of point in different directions. They can be little arrows or somewhat more complicated entities that are localized at every point in space. And they can be switched on or off, or they can be turned, like they have sort of geometric features. They can be turned a little bit. Some of those geometric features are sort of pointing in physical space. Some of them are a little bit more abstract. But roughly speaking, they're like localized intensities, or I like to think of them as like brightnesses at various points in space. And the pattern of which places are more or less intense, that varies from snapshot to snapshot. Those are the states. Those are the different states of affairs. The electric field, the classical electric field is a very good example of this. The classical electric field is the assignment of little arrows to every point in space. And those arrows have an operational meaning. They tell you what kind of force would be experienced by a charged particle were it located at that one point in space. If at some point in space the electric field assigns a very long arrow pointing in some direction, that is telling you that if you put a point charge there, it will feel a very strong electric force pointing in that direction. So this gives an operational meaning to what those arrows are, but we usually think of the electric field as just being there in space, attached to all these points. That may be the physical picture, but it is a physical picture of things at locations in space that change with time. And then the question is, can we write down dynamical laws, which are the rules that tell you how those snapshots are supposed to change with time? That, generalize F equals ma, Newton's law, which is the dynamical law for Newtonian objects, that tells you when you exert a net external force on them and the object has some particular inertial mass m, what acceleration it will experience. That's the dynamical law for a Newtonian body. The Maxwell equations are the dynamical laws for classical electric and magnetic fields. They tell you how charged particles and moving currents of charged particles generate electric and magnetic fields. And then in turn, there's a connected law, the Lorentz force law, that tells you how those fields back react or influence or exert influences on the particles. Those are the dynamical laws of classical electromagnetism. What I'm trying to do is provide a suitable set of dynamical laws that, when combined with an actual physical picture of real things in physical space, will end up reproducing the predictions that come out of the Dirac-von Neumann axioms. But now they would allow us to actually to say there's an actual thing going on. There's a process really unfolding between the measurements. This is no longer a merely instrumentalist, a means to an end kind, the ends justify the means kind of approach to quantum theory, where all we care about is the measurement results. We can actually say, no, there's a process unfolding between the measurement results, and that is responsible for the outcomes and probabilities associated with measurement results. So I think that clarifies my view. Physical reality, but we just need to find a better set of laws by generalizing a little bit what we think laws can be.
I should have placed a wager. I was the one who said that you believed in things.
Well, I mean, I think that we're both sort of right here, because from what I can tell in your lectures and talks that I've looked at, you're trying to make a classical representation of these processes to some extent, but classical representations also include reifications often, like forces as actors, like particles as physical objects, like fields as physical actors as well, right? Which I understand the utility of these reifications. They're incredibly advantageous technologically, but so I can see that you have this valence for the hope that these things are describing some physical processes, but that the laws that we'll use to describe them may not necessarily supervene on physical bodies doing things still. In other words, we wouldn't necessarily, in your work, have to posit any particular structures for these entities in order to produce stable laws that held across these different scale domains. Like, you don't really care what these fibers are or whatever it is that's down there, like that the atom's made out of or whatever it is.
I mean, I care that there's something.
Nice.
And it would be nice to know exactly what that something is. Could be fields, could be some other kind of microphysical ontology that we don't yet know. I'm not proposing a theory of everything, to be super clear. I think we have to be modest in science and in philosophy. There are a lot of very difficult problems, and I think we can't claim to be solving all of them. I'm trying to solve, I think, actually a very narrow problem. I think it's an important problem, that's why I'm working on it, but I don't think it's everything. I'm trying to eliminate the measurement problem and turn the textbook formulation of quantum theory into something derivable from a world picture. The upshot of this is not to tell us what quantum gravity is, or to explain all the mysteries of the brain, or where the universe came from. I mean, there are all other kinds of scientific mysteries that will persist here. I'm engaged in, I think, a somewhat more narrow task, but I think it's an important one, because I think abandoning world pictures, abandoning ontology, has a moral cast.
Yeah. All right. Now we're cooking.
That's his favorite topic.
First of all, I really appreciate that you're constraining the ambition that you have with any individual project in science. I think too often people try to say too much and end up saying too little as a result of it. But yeah, let's hear your moral angles. I mean, I completely agree. I could expound on that as well. I'm dying to know what you mean by that.
In any formal logical system, once you admit into your axioms inconsistent statements, you run the risk of, in an actual logical system, you invalidate everything you're trying to do, right? Everything can become inconsistent.
This is why you have to tell the truth, kids.
I think you have to strive to be honest. It's not that I'm not certain of anything. I mean, I'm not certain that there is a world picture to be had. But I think we should be trying to find one. The moment you give up on something this important, I think it doesn't always lead to good results. It's not that we can ever know for sure, but if you approach some scientific question and your answer is just, let's not bother investigating, maybe it was done by God, or maybe it was done by aliens, or maybe there are infinitely many parallel universes in which this thing shows up in various ways. And so inevitably there was going to be one in which it showed up in this way, and that's the one we happen to live in. These are all cop-outs. And it's not that we know they're false. We can't know they're false, any more than we can know that each of us is not really a brain in a vat, and this is all just sort of a dream or something like that. But I think it's very important for science that we try. We don't always succeed, but look at how far we've come. Think about how much progress we would have missed out on if at some earlier point we had simply given up.
Yeah, you should read the stuff that was written about Thomas Young when he contradicted Newton, you know?
Yeah, the young doubles, the original doubles that experiment.
Yeah, right.
Yeah.
I mean, I feel like there's something really sad about saying to our progeny, to our students and our children, that these things are unknowable, don't worry about them. That's kind of the angle I come at it from. It just seems like it's just sort of eviscerating, like you're just taking the fire out from under people who, you know, maybe I don't understand it, but maybe somebody else will. At least I'm willing to advocate that hope is worth maintaining for the betterment of all of us.
Yeah. I mean, in the development of quantum theory and the development of relativity, in the development of early 20th century, late 19th century, early 20th century physics, people really cared about what was going on down there at the bottom of reality. Like, They really cared that there was a world picture, that was something happening there. This isn't to say everybody was worried about it. There were debates about, how important is it to talk about things that may be in principle unobservable. There were debates about logical positivism, and there were people who took different sides of this. It would be wrong to say that everybody was concerned with trying to construct a clear ontology of, fundamental reality. Not everybody was, but some of them were. And even the ones who weren't, by engaging with those who were, you got the generation of important scientific insights. I think it's grounding. Once you let go of the idea that we have any responsibility to strive for trying to construct an ontology, a world picture, I think you shed a certain kind of responsibility.
Is this where your opinions on causality come in?
I don't know that my views on causality are necessarily connected to this particular point. Maybe tangentially.
I mean, I can imagine that they are, just on the level of this obligation to try, this obligation to strive, and an obligation also to take some ownership or shoulder the burdens of outcome.
Yeah.
And so if you live in a world that is either fated to go one way because of the fact that there's no such thing as free will and everything is just kind of, you're passing through some path that was predetermined for you, I think that they're somehow related, because the idea of striving for good, for aiming for something that is an improvement over what we have right now, seems to hinge on causality being real and you being able to take an action that shifts the arc of the world.
Yeah, that we have causal powers as beings
as agents.
As agents, that we're agents, that we have the capacity for free will. I don't have an answer about whether we have free will. Like I said, I'm not trying to solve every problem. There are a lot of problems that I'm not going to be able to solve. I don't know whether we truly have free will. In fact, even rigorously defining what exactly you mean by free will turns out to be very thorny. There are a lot of deep philosophical problems in which even specifying the question in a rigorous, non-circular way turns out to be extremely difficult. What is free will? It's the free, I can't use the word free, it's the capacity to make decisions and control one's fate. But what do you mean by make decisions and control one's fate? Well, to choose. I can't use free choice. Okay. Like, the words are all kind of interrelated with each other.
To move against gravity.
Well, all kinds of things move in the opposite direction to the gravitational field that don't have free will.
Like photons.
Yeah, I mean, small bits of dust get swept up by the air and they go up in the sky against gravity. Things rise in a gravitational field.
Okay, so what about, like, to move against the path of least resistance?
Again, many things move against the path of least resistance that we don't ascribe free will to. If you're asking, does free will mean you can violate the laws of physics? Well, you can't choose to not be subject to energy conservation near Earth's surface. You can't just choose to not experience downward acceleration in a gravitational field unless you apply some other force. But you can't just choose to not obey Newton's laws if you're a macroscopic object moving at non-relativistic velocity.
Sure.
Like, we can't just float up out of our chairs. But we can stand up, which is pretty weird.
Well, it's amazing we can, because all of Earth is pulling down on us.
Right.
And with our puny electrochemical reactions in our muscles, we're able to overcome gravity. In fact, if we had a tall enough ladder, you could just keep climbing. That's kind of amazing that all of Earth cannot stop you from doing this.
I will say, as someone who's climbed a 13,000 mountain, it's much harder to keep climbing at some point. So,
but you can lie down and rest, right?
It's true.
And then you go back to climbing. I mean, do it all in one go. Sure, you will use up the energy stores you have, but you bring food and you sleep, and yes, of course. And then you have to deal, of course, with, if you get high enough, you have rarefied atmosphere and there's no oxygen.
But so hard. Yeah. At some point, you just get to the place where you're like, do I really want this that bad? That's the gravity of the Earth pulling you back down.
But did you have any revelations when you'd gotten at that high altitude?
I did.
Yeah.
This is a godforsaken place that no life was meant to be at. You just get to the top, and it's just this barren, broken mass of rock. Like, even the animals don't, and even the mountain goats don't go that high.
Yeah.
And you've achieved something, but they spend a lot of time contemplating. Oh, it's excellent because in the Pacific Northwest, you glissade down the mountains, and so you come to the top, and then you basically sit down and you slide 2,000 feet in 10 minutes, and it's extraordinary. So it's a very good snow sled.
So the goats know not to go that high. Why are humans so foolish that we don't do what the goats do?
I don't know. We're going to Mars too. I think it's the same impulse, the same culture that climbs.
Who's we? I'm not going to Mars. I'm pretty happy here.
Yeah, it's true. Well, and you probably would not enjoy mountain climbing either. I'd recommend against it.
So I want to go back to this this substrate level, this world approach. Have you? Okay, so my background's in material science, elastic mechanics, atomic force microscopes. Everything is essentially, materials interacting with one another. It's pretty simple. There's the interactions between their subunits kind of define their material properties. And I'm actually struck by, especially studying cantilever dynamics, how similar a lot of the basic oscillatory phenomena is to the quantum world.
So these cantilevers are these little, very tiny diving boards, right? They look like little diving boards, and they're so tiny, they're like down at the nanoscale, and
and you process those vibrations in such a way that you study how they interact with the environments locally, and you can derive a lot of information about the material properties of what they're touching. And a lot of those mathematics are actually quite similar to electrodynamic equations, transport functions in general. There's so many really interesting parallels, and I know people in the 19th century and before tried really well. Let's stick with the 19th century and the turn of the 20th century. I know there was a lot of really diehard attempts to make sense of the substrate level in terms of elastic mechanics. I believe there was a Scottish physicist, I think his name was McCulloch, who tried this at some point. Of course, Maxwell famously tried these vortices. What was the problem with all of these approaches, you think, that led people to abandon them? Or was it simply just the overwhelming success of the abstract mathematical approach at the end of the day?
I mean, I can talk a little bit about the vortex theory that Maxwell worked on.
Sure.
Lord Kelvin was pretty excited about it as well. So a natural question you can ask about electromagnetic fields is, well, if you perturb electromagnetic fields in the right way, you can generate a disturbance that propagates like a wave. And this propagation is described mathematically in terms of a differential equation that is called the wave equation. It's like a beautiful, beautiful manifestation of the wave equation. It shows up coming out of the Maxwell equations, the dynamical laws for the electromagnetic field. And an immediate question you can ask is, well, if it is a wave, what is the medium? Waves that we see around us are some material moving up or down or forward and back. There's some kind of localized disturbance in some physical medium, the substrate. And the wave is not a separate kind of ontology. It's not some separate physical thing. It's just a pattern of the behavior of the medium that looks to our eyes like something moving, but nothing is actually going anywhere. An example is a slinky. I've got a slinky right here. If you have a slinky and you stretch it some distance, you can shake it, or up and down, or forward and back, and you'll see what looks like some kind of thing propagating from one side to the other. But no physical material is going from one end of the slinky to the other end of the slinky. The metal is not moving from the first end all the way to the other end. it's just stuff in the slinky either going up or down a little bit or forward and back a little bit. Every part of the slinky is only moving little bits, oscillating little bits, but what's being propagated forward are certain conserved quantities like momentum and energy. So a natural question is, if there are waves that you can generate in the electromagnetic field itself, what's the medium? And the idea was the medium was a material. This material suffused all of physical three-dimensional space. It was called the luminiferous ether, the light-bearing heavenly substance. And people became quite concerned with its material properties. There's a quotation in Max Born's autobiographical memoir, My Life Recollections of a Nobel Laureate, in which Max Born talks about how around the turn of the 20th century, people thought they understood the ether so well that they thought they understood its material properties better than the properties of regular matter. Famously, Einstein banished the ether, removed it, said there was no ether. There are a variety of experiments that made it very difficult to think that there could be an ether. The Fizeau experiment, the Michelson-Morley experiment, yeah.
He considered space-time to be a non-kinematic ether.
Yeah. I mean, you can regard in general relativity, Einstein's theory of curving spacetime, that spacetime is itself a kind of material with kind of material properties. But the kind of ether that they were talking about at the turn of the century was a material fluid suffusing space.
I think the all-pervasive piece of this is critical, actually.
Yeah. Now, the thing about the ether is that there were equations that describe the behavior of this ether, and these equations took the form of complicated partial differential equations. And these partial differential equations appeared to have non-trivial, geometrically shaped solutions in them, these swirly solutions that were called vortices. And Maxwell wrote a lot about these vortices. And the idea was that maybe these strange configurations of the ether stuff, the ether fluid, interacted, moved around, and maybe they could even be what material particles are. So that we would have our first example of a mathematical unified theory, a unified field theory. Light and electromagnetic waves were depressions and disturbances in ether, and vortices and knots and loops of ether fluid were material matter. And people like Tate developed a whole mathematics of these vortices. These vortices could like curl around each other into loops and form knots. And there's an area of mathematics called knot theory that comes out of this history, because they noticed that all of these knots and their geometric properties could be classified in a systematic way. There were even suggestions, if I'm remembering correctly, that the systematic way of classifying all the knots could be laid out in charts, and people thought maybe this was like what the periodic table of the elements was, that the atoms were ultimately just different geometric arrangements that could be systematized and organized into a table, and maybe this is where the periodic table came from. And ultimately, the ether vortex theory died off for a variety of reasons. One is that with the advent of special relativity, the ether was banished. There were all of these...
Could you just say it was unnecessary?
That was unnecessary, yes. But also, it was very difficult to maintain the ether hypothesis in light of various experimental results. I mentioned the Fizeau experiment, which is the idea that if light really is some disturbance in the ether, then if I shine light through a substance that slows down the speed of light, and I move the substance, maybe a tank of water, and I literally carry the tank of water and move it as the light is going through it, I can study how the speed of light can be added to the speed of the chamber, and you don't get the predicted simple rules for adding velocities. And then the Michelson-Morley experiment had to do with, as Earth goes around the sun, you consider light going in different directions, and you'd expect that the motion of the Earth would add to the motion. Earth moving through the ether would mean that sometimes Earth was moving in the same direction as the ether, sometimes other directions, and that light should be at different speeds depending which way we were oriented. We didn't see that. Eventually, the idea of the ether it was unable to accommodate all of these experiments. And you could have proposed some kind of relativistic ether or some ether that's not a simple mechanical kind of substance, some much more abstract kind of ether. And if you're willing to do that, well, then you can do almost anything. You could imagine that there is a kind of ether that doesn't have all the properties the original ether was supposed to have, but at some point you begin to wonder, do we even need this anymore?
Isn't a key aspect of the luminiferous ether that it is distinct from matter? That
Yeah, I was going to say, like, the third option might be to consider that the medium is not distinct from the atoms themselves that are participating in it.
That's the vortex theory. The idea that the atoms are in fact manifestations of the ether itself. Yeah.
Except that there's a pervasive substance, right? That it's this continuum substance that fills all of the voids, right? Which, from a materials science standpoint, leaves little room for motion if you don't have subunits articulating in some void to process through.
Well, I mean, they would say that the vortices moved. You got these knots in the fluid, and you could, the vortices could travel and maintain their sort of geometric structure as they moved. And if you zoomed out enough, you could see what looked like a point-like disturbance of energy, and that this is what particles really were.
So if relativity displaces ether, and I mean, with the Michelson-Morley, there's some indication that I think it was Michelson who went and like in the 1930s, he built a much larger interferometer and he seemed like he did detect the ether drag. And so when you trawl around on the internet, you find plenty of people that are like, hey, hold on a second, it wasn't actually disproved, it was just this one experiment. So with the dominance of relativity and the bending of space-time as being this thing and that replaces the ether, do you think that that's something that deserves revisiting, or do you think that that some sort of substance that waves is possible to have alongside of relativity? Like, how does that work for you?
I want to make clear, because we are talking a lot about the history of relativity, that I am not an expert on the history of relativity, and some of the statements I'm making should be fact-checked.
The internet will take care
We have a professor here at Harvard, Peter Gallison, who is an historian of science and wrote a book about relativity and the history of relativity. There are definitely people who know more about this than I do and may point to things I've gotten wrong. So I want to be very clear to anyone who's like listening to this that about the history, please take the things I'm saying with a grain of salt. What I will say is that science is not clean. There are not clean endings to theories where it's just very clear the theory is wrong, we move on and everyone just drops it. Almost never. I mean, I'm sure you could think of examples. And there are no situations in which we identify the correct theory instantly and we're sure it's the correct theory and we're just done. Science is a very messy process. I make a distinction between scientists and science. I think some people are apt to say that science is just scientists. The sociology of scientists, what they do, that's all science is. I'm idealistic enough, in the pedestrian sense of the word idealistic. I'm not a philosophical idealist.
Thank goodness for that.
I'm not a philosophical idealist, but in the colloquial sense of idealism, I'm idealistic enough that I think that science stands apart from the humans who do it. Science is a methodology, a way of thinking about the world, a way of probing the world that is beautiful and extraordinary, and I've fallen ever more in love with it as time has gone by, both as a philosopher and as someone who's been trained in science. And to the extent that I have been, like anyone, frustrated and disappointed sometimes with the humans who conduct science, I don't see those as the same thing. I think science progresses. I think we do have a better understanding of the world, scientifically speaking, than we did in the past. In many respects, at least. And I think the fact that humans often do science imperfectly doesn't mean that science as a thing, as a methodology, as a way of knowing about the world, as a body of knowledge, as a form of inquiry, is any lesser.
Yeah, well, it's supposed to be progressive too, right? Like it's supposed to be wrong iteratively. Like people kind of forget that sometimes when they impugn, whatever particular branch they're picking on. It's like that's kind of baked into the cake of what science is supposed to be.
When you walk around thinking that you have all the answers already and don't need to subject them to experiment, don't need to subject them to rigorous analysis, and are unwilling to listen to criticism, it's easy to look at science and think that science is an inferior way to know about the world. When science is done well, it is open to all of those things. And so we see the error, we see the mistakes, the missteps, we see sometimes periods of stagnation, sometimes even periods of loss where things have stagnated and people have forgotten how to do things. But I still hold that of the methods we have for inquiring about the natural world, it's still crucial and vital, and I think that it is making progress overall. I think acknowledging the shortcomings of science is a matter of humility, and I think we need to be more humble.
Yeah, I think epistemic humility is at the core of trying to understand anything. And if we attempt to bludgeon one another with one dogma to replace a dogma that we dislike, I think that we just end at greater and greater crises.
Yeah, I mean, like we were talking earlier this morning, just about how there's a lot of different ways to describe this incredibly complex experience of being a being, right? And I think that if you tried to interact with your wife or something on the order of physics exclusively, you might not have a very happy marriage. And I feel like much of the world is like that. You need different tools for different jobs. And so we started off, talking about some of the shortcomings of quantum mechanics, but also sort of the unreasonable demands put upon it as this theory of everything. And there's so much happening in this room right now that quantum mechanics would just not be the appropriate way to comprehend.
Yeah, I agree. I was trying to be as precise as I could before in talking about quantum mechanics as a purportedly complete theory of microphysical reality. All those terms were chosen very carefully. I don't think quantum mechanics is the right theory to talk about psychology or human behavior or sociology or politics or many of the things that matter to us, let alone art and poetry and ethics. These are distinct things. Knowing where the atoms are and what they're doing is not going to tell you how important it is to save someone from danger or how to decide between difficult ethical alternatives, right? I mean, these are just totally different categories. Anyone who thinks that you can derive ethics in some purely scientific or logical way does not understand ethics.
It's funny, because that's the complete opposite approach of Stephen Wolfram, who we were sitting down with yesterday or the day before, who believes that everything is essentially calculable. And it's funny because we were talking to some AI researchers, I forget who this was, but they were doing training sets to figure out these self-driving cars, how they make decisions between, hitting like 3 grandmas or like 1 baby and 2 20-year-olds. Like if they have to veer around something, like how are they going to do it? And so they're actually trying to calculate ethical situations. And it's kind of a nightmare because the only thing you can do is basically put it in front of human beings who make some judgments based on the whole wealth of their experience on Earth and their value structures and their cultures, and then sort of integrate all of this data into some, trained module of how it should respond. But it didn't seem calculable on its face using first principles or axioms of any sort.
I mean, Rebecca Goldstein is a philosopher and author, wrote a very popular book called Plato at the Googleplex, which I enjoyed. If people want a book recommendation, they can look at it. And the hook of her narrative is that Plato has somehow reemerged in contemporary society and is walking around at different venues, interacting with people, and really basically saying things that were in his writings. We have a comprehensive set of all the things that Plato has written. We actually have all the texts. And he just basically applies many of the things that he was saying back then to today and pokes holes in people's ambitions to have solved philosophy or to have done away with the need for philosophy. And the first thing he does is he goes to Google in this narrative, and he talks to someone who says that they've solved morality, using some combination of crowdsourcing and software. And Plato just totally destroys this whole idea, right? That ultimately, I mean, people have been talking this a long time. I don't want to contradict anybody personally. I don't want to make any sort of personal criticisms, but I will just say rather boldly, you're not going to solve ethics through some sort of calculation that doesn't begin with ethical axioms.
Understandings in the first place, yeah.
Any deductive logical argument begins with premises,
Assumptions.
the assumptions, proceeds with rigorous logical steps, with rigorous reasoning, and then arrives at one or more conclusions. If the logic is tight, then we say that this is a valid argument. If the premises are credible and the argument is valid, we say we've got a sound deductive argument. Mathematical proofs take this form. But it's important to know that in a deductive argument, in which the conclusions unavoidably follow from the premises and logic, the conclusions can never be fundamentally stronger than the premises. The conclusions are, in some sense, rearrangements or reveal things that were inherent in the premises to begin with. You can't arrive at ethical conclusions from premises that are not initially ethical. And you can't get around this through any amount of hand-waving. You can't just write an argument that's sufficiently complicated or plug into a computer and somehow get around this. This is a fundamental obstruction. And I think it's important that we not claim that we can avoid having to contend with ethics. I think that is an attempt to absolve ourselves of a very important responsibility. We have a responsibility to try to be ethical. And that's really, sometimes really hard.
Do you differentiate between ethical and good?
Ethical, I'm just taking ethical to mean a set of methodologies or frameworks or system of analysis for trying to weigh the way that we ought to behave, the decisions we ought to make. It has that word ought in it, right? These sort of statements about what we ought to do or what we should do in order to uphold some notion of what it is to be moral or good. But whether a particular ethical framework is moral or good is not something that I can definitively answer. I don't know the definition of what good is, in some general sense. I only have my own premises about what I think is good, and the conclusions I've arrived at through thinking carefully about my premises about what's good.
But science can't offer that. And that's, I think, the biggest crisis, which is that without a constant conversation that one must determine what is good for oneself. Like, let's take away the idea that there's a universal good and just say that one needs to have a system for oneself that differentiates that and defines it well enough to be able to live by that.
Yeah.
Like, science can't do that. Science can't give that. And you wander into scientific spaces and technological spaces and you realize that we talked at the beginning about mythology.
Yeah.
And I want to differentiate mythology versus mysticism, because I think that mysticism is very dangerous. I think mysticism is the snake oil salesman that hypnotizes you into buying the potion that will cure everything, which is why we're DemystifySci, because it's about, like, let us remove the mysticism, let us remove the snake oil from this equation. And yet, I think that mythology is incredibly powerful, because mythology is the story of what happens to us when we forget to aim. And when we fail to aim, or when we aim for the wrong things. And that's the beautiful thing that lives in parallel with science and cannot be subsumed by it or derived from it. It is literally it is spirit. And I'm like, let us take the spiritual weird stuff out of quantum mechanics and put it somewhere where it might make more sense. As a biologist, I want to put it into biology because I'm like, I think that is what life is. I think that this is actually, I'm going to drop this in the last, 10 minutes. I think that the ability to decide what one wants to be is the thing that differentiates the tree from the grass, from the human, from the bird, from the wolf, from the dolphin. Nobody else agrees with me. And I recognize that, but I still think that this is so vital to the turning of the earth that science literally cannot incorporate in it It cannot incorporate it in any discipline that it has, and yet I think it is central.
I want to make clear here that just because I don't know what good is and I'm struggling myself doesn't mean I don't believe that there is any objective notion of what's good. There's a long-running debate about whether people are moral realists or moral relativists, or there are all kinds of philosophy. I don't have the answer to any of that. I'm not purporting to. I'm, as you put it, an epistemically limited being. We all are, and we have to approach these subjects with a certain degree of humility. That we're never going to maybe know what that is. I would even go so far as to say that anybody who claims to know with certainty what is good is a dangerous person.
It's a lot easier to say what's evil than what's good. A lot easier.
That may be true.
In extreme cases, at least. Yeah.
But even then, there's some things that have, some areas of science that some people have called evil. I mean, it's not always so easy to say what evil is. I mean, certainly some kinds of science have done very bad things, but there are other people who have said that certain areas of science I think that are very good are things that humans shouldn't be involved in trying to learn more about.
I will say that I will occasionally read books about neuroscience, and it's a struggle.
The slaughterhouse.
It's dark.
I'll just say I think we're on safe ground by saying that biology is where life is happening. I mean, that's a statement I'm willing to get behind, but not all of life. I mean, I think there are some aspects of life that are not capturable in biology either.
What do you mean?
Is poetry not part of life?
Music.
Art, music, are those reducible to biology? I don't think they are.
I don't know a lot of rocks that make.
I mean, you can see a lot of music in the sky if you look hard enough.
I don't mean.
I
But you see, what you conflated biology with life because you're just like, well, rocks don't make it, and rocks aren't biology. That doesn't mean that just because rocks can't make art and poetry, doesn't mean that art and poetry are derivable from biology either. I don't think you can use biology to derive Shakespeare.
As like a process of understanding the world.
Sure. I'll take it.
As a process for understanding the world. I think there is something else there. I don't know exactly what it is.
But it's probably not just quantum physics.
It is not just quantum physics. If we knew where every single atom in your brain was and what it was doing,
you still wouldn't write Shakespeare.
It wouldn't explain why you decided to do a particular thing, or why you love a particular person, or why you believe a particular. I mean, you'd be able to say, okay, I know the atoms are. If I have all the rules, I can predict the next place the atoms will be, or at least probabilistically say where the atoms will be in the next possible place. Maybe with suitable averaging, I can say somewhat more determinative statements about the averaged behavior of the system. But if someone says, okay, you've predicted what the system will do, now why did the person you're modeling believe these things? That's not written in the atoms. It's something else that requires a different kind of analysis.
And it's weird because I think that we are the cultural products of an intellectual tradition that was overtaken by this supernatural institutional religion that then had to be argued against. And we are now at the back of that arc, where we have argued against the religious teachings. We have laid out why they do not belong in science. And now we're stuck with this question of, oh my goodness, how do we fold something back in that is sufficiently robust and meaningful that we can still keep this entire edifice of the neat picture of science and calculation and theory, and yet have something that is next to it. And I think the dualism is very uncomfortable for people. And yet it does seem inherently...
Can I ask you a question? You described the scientific picture as neat.
Oh, I think that people do try to make it very neat. Have you ever picked up a textbook?
People may try to make it neat.
But
people try many things. I think science is a complete mess, and I think that's okay. I mean, you have to get a little messy to be creative.
So is poetry and music and mythology, right? I mean, you listen to a great album and it's got every perspective on some behavior set almost. It's like this person's going through all these terrible decisions and these outcomes, and then maybe they're figuring it out, but then they forget. And that's like what a really good drama, even like an epic poem or a epic piece of literature. It's like just this long winding road. It's a mess, really. But there's some thread in the way that the characters navigate it that teaches you in the process. And science is kind of the same way.
Yeah. I think that this is a fantastic place to put a pin in it. I know you have to go in 6 minutes, but I don't.
How would you like to close our conversation?
That's a great question.
I think we're going to just have to have another conversation at some point.
Maybe.
Yeah.
Let us leave it open because there's just so much left on the table. It's been a real pleasure, and I just cannot say thank you enough because you've taken time out of your day and have found space for us and allowed us to bring such chaos into your space that I'm very grateful.
It's hard to say no to what you both seem like such lovely people.
Oh.
And, I don't really know what to say about all the challenges we're facing right now in science. Science is in a very difficult place right now. I don't want to be political in any of my comments, but things have really begun to push into the practice of science. I don't have an answer for these problems. I don't know how to solve any of this, but I do think there are some things that we should do. I've been thinking a lot about how we should react to living through challenging times. One of those is I think this is a moment we have to think very carefully about the importance of being human to each other. I think a lot about how I'm interacting with the people in my life and whether I'm being sufficiently human to everybody. I know that being human is a complicated thing. Sometimes humans do things that aren't very, very good, but I mean human in the best possible sense. What are the things about humanity that we think are good? I mean, there was the word good. The things about humanity that we admire and that we think make humanity worth saving. And I'm trying as best I can to think about how I can be human to the people I care about. The second is, it's very easy to focus your attention on what you think is being lost. But if you focus all your attention on that, it can be demoralizing and it can lead to despair. I think this is a moment when we have to all be thinking about how we can build things. It may be difficult to build things right now. We do face constraints and limitations of all kinds. But I think that in almost every situation, if we think hard enough, we can figure out something that we can build with what we have at our disposal, ideally with other people we care about as a cooperative project. And that to build something in difficult times is to create the hope that we need.
That's beautifully said.
Amen. Yeah, absolutely. 100%. 100,000%.
I think that's what we're trying to do here is also deeply to be human, because when you make YouTube videos, I think that there is this sense of putting yourself into the machine as like grist for the mill. And we run into people that are very much doing this for views and clicks and attention and all of these things that I think are deeply demoralizing to the world. And the basis of this project is to find people that are aligned with the project of, let us create a space where we can share ideas. Let us create a space where we can elevate each other. Let us create a space where
we can search for ideas that might set us on a better track eventually. Really, we don't, we never know when we sit down for one of these conversations whether we're going to stumble into any of them or not. But everybody who's on board is willing to stick it out and see.
Yeah.
Well, you seem to be the kind of people who have an idea of what you want society to be like, and you're living yourselves. You're trying to act in the way that you, I mean, this is going to sound a little Kantian, I guess, right? That you're trying to do the thing that you hope would be universalized and we would all do. But you're trying to make something that is informative and interesting and will bring a ray of sunshine into the world and inspire. And if everybody did the thing that you were doing right now, I do think the world would be a better place.
There's a million paths to that, and I believe that everybody has one. You just gotta tune into it, put your back into it.
Yeah.
But I think you have to try.
Yeah, that's the first step.
I think it's more important to try than it is even to succeed. You have to really be trying all the time.
There was, I came across this quote that one must imagine Sisyphus to be happy.
Yeah, that's Camus.
Exactly.
Yeah.
And I keep turning to it where I'm like, it is, you wake up every morning and you roll the rock up the hill and you just figure out how to be jolly. We went to go visit one of our mentors, and his car had a license plate on it, which was "Be Jolly," and this is ever since then has been the central feature when one of us is grousing. It's like,
Can I ask you a question? How do you think Sisyphus would feel if he managed to get the rock to the top of the mountain?
Wholly empty and unmoored.
And then had to face eternity with no longer even having a rock to push up a hill.
I think he would push it down.
I think we've seen this before. I think we've seen this in people at the end of their lives sometimes, yeah.
Yeah, I think
It
that the rock
happens.
is central. Oh man, there's so much about this. Let's talk again.
Yeah, we have to get you off to your meeting.
Yes.
It's a real delight. Thank you for taking the time to talk with me.
Thank you.
Thank you for considering me to have anything useful to say. I
Oh.
really appreciate it.
No, you have plenty. All right, let's put this place back together.